we will solve an example to see one important effect which we have been repeatedly mentioning, that is the increase in area per unit volume of particle. So, we said when you go to nano sizes, at least one important effect which is obvious and which is expected is the increase in surface area. And we had noted that suppose instead of talking about only the external surface and we are talking about a polycrystalline material and we are actually reducing the grain size, then the interface area, which is the grain boundary area per unit volume of the material, will increase as I reduce my grain size to very small dimensions. So, let us make a calculation to understand this effect, so that we have in perspective the kind of numbers involved and the effects we are talking about. At the outset, there are two effects which you expect when you go down to small scales. So, two important things we have to keep in mind when we are actually reducing the particle size. One is that the surface area per unit volume will increase, and we will actually make a calculation to show this, but additionally we will notice that curvature effects start to dominate when you go down to small sizes. So, if you had a large size particle, this curvature here would be actually small as compared to a small size particle. As you know, curvature goes as the inverse of the radius of curvature. Therefore, as I reduce my particle size and make the radius smaller, the curvature effects will start to dominate, because now there will be more unsatisfied bonds on the with respect to the surface atoms here as compared to a case where the curvature is small. So, these two important effects will start to dominate when I go down to small sizes, and this example will particularly focus on the first one. So, let us calculate the surface area as the size of the particle is reduced. Let us assume that the particles are spherical for now, and we will all later on take up a couple of more examples of what other possibilities exist and find out the effect of increasing the number of particles keeping the total volume constant. Let us start with one particle of volume V1, and if you assume the radius of the particle to be 1 unit, then the volume will be 4 by 3 pi 1 unit cube, which is 4 by 3 pi. The area of the particle, since there is only one particle, and the subscript here refers to the number of particles. So, the subscript in these cases refers to the number of particles at each stage of my what you may call division, and that will be 4 pi area units. The area per unit volume, if I calculate, is A1 by V1, and since I have only one particle at this stage, it is 4 pi r square by 4 by 3 pi r cube, which is 3 by r. That means, if I keep reducing my r, then area per unit volume will increase. Now, what will happen if I divide this particle, and here I am talking about a division like this, where I take a single particle, divide it into two particles, further divide this particle into 3 particles if necessary, and to 4 particles. So, there are 3 particles at this stage, there are 4 particles at this stage, and I keep on increasing the number of divisions, but at each point of time I keep my particle spherical, and I also keep the total volume that equal to the starting particle. So, these are the two constraints I impose. So, I notice that the area per unit for one particle is 3 by r. If I split this particle into two spherical particles of equal volume, from volume constancy we get that 4 by 3 pi r2 cube, which r2 is being the radius of the smaller particle, which is got from dividing the larger particle, and there are 2 of these particles. So, the number 2 is coming from the fact there are 2 of these particles. Then I have 4 by 3 pi. This implies, and this is the original starting volume, that means R2 is 1 by 2 power 1 by 3, which is 0.79. So, if I divide my 1 unit radius particle into 2 particles, the radius of those particles will be 0.79 units. The area now is twice, because there are 2 particles, into 4 pi r square, which is 4 pi into half power 2 by 3, because we know now that R2 is 1 by 2 power 1 by 3. Therefore, I get 2 into 7.92, which is 15.84. So, I got 15.84 as the area in the second stage. Now, I would like to do this truncation repeatedly, and therefore, I would like a formula for any number n, a general number n of particles, and in that case I can calculate the relevant quantities as Rn being the radius at the end stage of division, Vn being the volume at the end stage of division, An being the area at the nth stage of division, and I can actually go ahead and calculate the area per unit volume at the nth stage of division. So, let us see what are the relevant formulae here. Rn is 1 by n power 1 by 3. So, at the second stage it will become 1 by 2 power 1 by 3 as we had seen here in the case of the first stage of division. So, this is the case for the 2. So, suppose I am talking about the fifth stage of division, it will become 1 by 5 power 1 by 3. The volume at the nth stage would be 4 by 3 pi r cube, r being 1 by n. So, it is 1 by n power 1 by 3 cube. So, it is 1 by n. Therefore, the volume at the nth stage is 4 by 3 pi into 1 by n. The area at the nth stage, now we have n of these particles, therefore, I am calculating the total area. Here the volume I am referring to is the volume of the particle, individual particle, and not the total volume, which anyhow remains constant even if you divide into n number of particles, because we are starting with the given volume and dividing into smaller and smaller volumes. Now, each of these particles will have 4 pi r square, which is 1 by n power 1 by 3 square, but then n of these particles will contribute n times that area, and that is what I am writing down as A n here. So, it becomes 4 pi n power 1 by 3. The area per unit volume then goes to A n by V n is 3 n power 1 by 3. So, if I now plot these quantities to get a feel how these things changes. So, the plot is shown here. This is the number of particles, and initially I am starting with small number of particles, like starting from 1, I go to about say 17 particles here. And if I have two relevant quantities, the primary axis refers to the total area of the particles, and the secondary axis refers to the area per unit volume, which is this formula here. So, this is my secondary axis, and the total area of the particles is plotted as the primary axis. So, we notice that the total area of the particle starts from about, if you look at the formula here, it is about, we start from somewhere around about more than 10, and this is the total area given by this upper line, and you can see that the number increases, and by the time we go to about say 16 particles, already the area has increased more than double. So, you can see that this number is close to double, and we see that even when you are about more than 16 particles, or we have divided the original part in 16 times, the total area has gone more than double. If you look at the area per unit particle, then this is now my secondary axis. So, you see that initial starting value is 1, because that is what my starting area per unit volume is, and then I see that it has gone to value of 3. So, there is a 3 time increase, approximately 3. So, let us do this calculation a little more and try to understand the impact, especially when I go to large number of particles as shown in the bottom graph. So, you are starting with one particle and going to something like a few thousand particles. Here we have shown about 9,000 particles, to see how these numbers change and what will be the impact of this increase in number of particles. Before we go to such large numbers, let us do our calculation in terms of percentages, because often it is very important to have a number that if I reduce my particle size by a certain value, what is my overall percentage increase in area, and especially what is the percentage increase in area for a given volume of material I start with. So, the percentage increase in area is the curve which is plotted on the top and which is referred to in the primary axis. So, the primary axis refers to the percentage increase in area. So, initially of course, there is only one particle, and therefore, the percentage, there is no increase in percentage. We are calculating the increase in percentage with respect to this one particle. But the important point to note is that when you are about, for instance, just about 8 particles here, you see that you already reached an 100% increase in area. So, all I have to get is 8 particles from one particle before I already see a 100% increase in surface area. This is a very important effect. That means that that as I go dividing more and more, my percentage increase is expected to be more drastic, and that is what is the usual goal of producing nanoparticles. Now, the radius of the particle is an important number to note here. You see the radius of particle is not changing much. If you refer to the previous calculation, when we had 2 particles, the radius is 0.79, and this can be better seen in a figure like this, that at each stage these particles are not looking much smaller than the previous particle. The radius is not changing that drastically as compared to the surface area or percentage increase in surface area, and you can see that even when you have divided your particle about 18 times, the radius has come down to about only 0.4, starting from a radius of 1. That implies that the radius is not decreasing drastically, and of course, that is directly a consequence of the way the function depends, it is 1 by n power 1 by 3, but my overall percentage surface area increases. So, let us see if I keep on dividing, carry on this subdivision of the one single particle into larger and larger number of particles, what kind of a reduction in area can I get, and we will later on carry the forward this calculation to see to represent these numbers in a slightly different way. So, suppose I start with one particle and I go to, for instance, a number like 9,000 particles, which is still a small number as compared to what is possible, and you would notice that the curve increases drastically, and by the time I am reaching a number like that, I can almost get a 2000% increase in the area. So, this is an important point to note, that if I take one particle and divide it into about say 9,000 particle, I get a 2000% increase in surface area, which is meaning that I am not change the volume of the starting material. That means I am having the same volume of the material, but I am just dividing the particle into sub particles, and my overall surface area is going to increase drastically. Of course, as I pointed out, that instead of starting with dividing the particle itself, I could actually talk about starting with a single grain material. This is a single crystal, and I can visualize this being divided at each stage into a number of grains. So, this could be, for instance, into 2 grains. Then I can think of dividing this. Of course, it is easier to start with the, for instance, a spherical particle to see the effect. So, let me do that. So, let me start with a single grain particle, and then I will divide into 2 grains, then I can divide it into 3 grains, and of course, I could keep on doing the subdivision, in which I will get a particle in which there are very small grain sized material. In this case, this is a schematic division. In this case, it is the particle size is not reducing, it is actually the grain size which is reducing, and this implies that my grain boundary area or my interface area is going to drastically increase. Now, this has profound consequences, like now we are talking about, if you are talking about grain boundary diffusion, or I am talking about creep dominated by grain boundary diffusion, then these kind of effects will start to dominate when I reduce my grain size to these values. Let us further extend the same example, wherein let us consider a spherical particle with radius equal to 1 millimeter. So, now this is now a tangible particle 1 millimeter in radius, and reduce the size to 10 nanometers. That means, now I am starting with a tangible particle and reducing the size to the nanometric scale. The number of particles can be calculated using volume constancy like we did before. That means that 4 by 3 pi, this is now my 1 millimeter particle cube, is n times, now n is the number of particles I would obtain, 4 by 3 pi into, now it is my 10 nanometer particle is 10 power minus 8 cube, that means that n is 10 power 15. Therefore, when I go to the nanometric length scale, the number of particles I will produce is humongous. So, this increase in area is one aspect of the thing, but also additionally we see that the number of particles is also huge. So, if I make an area ratio calculation, I would notice that there is a 10 power 5 fold increase in area, and therefore, these two aspects go hand in hand, and this implies that I do not need lot of material if I want to actually produce a large number of nanoparticles. It is just that I have to keep subdividing till I reach the relevant length scale for my problem. And this is directly leading to what we have been reiterating many times, that such a large increase in surface area implies physical properties will become surface dominant. So, there will be definitely a contribution from the surface in any one of the physical properties you are talking about, let it be plasmon resonance, let it be adsorption of gases, let it be creep in the case of a polycrystalline material. All this will be dominated by surface or interface effects. Now, let us do instead of doing a top bottom down approach wherein we are starting with a particle and actually cutting it down, let us start with something known as a bottom up approach, and this bottom up approach will throw into light certain other concepts, like when you take a nanocrystal, often it is not spherical. You may find that apart from it being non spherical, there are certain magic numbers which appear, that means certain magic number of atoms are stabilized. So, here we are considering what we may call a bottom up approach, and this is how many synthetic methods actually work. We do not start with the bulk crystal, but we actually construct the nanocrystal starting from a few atoms or a few molecules. So, this is a very important method of actual synthesis, and so this is, we should keep this kind of a technique in mind. The particles may be non-spherical, in fact they could actually be polyhedral, and if you are talking about roughening of shape, that means a well defined shape, if surface diffusion effects are dominant, then you will see that nanoparticles can easily assume that kind of a polyhedral shape. And there is an additional factor, that there are magic numbers which appear. This magic numbers may be stabilized by electronic configuration, etc., but here we will see that because of purely geometric reasons such magic numbers may appear. So, instead of starting with a bulk crystal and reducing its size, we do an bottom up construction, and as an example let us take an cubic closed packed crystal, and here we take the first coordination shell of such a crystal. I have here what is known as a shape which is known as a cube octahedron, which is between a cube and an octahedron, and it is the coordination polyhedron in FCC. So, around each atom, for instance I take a centralized atom, I can have 12 other atoms around it which are in the shape of a cube octahedron. Further to this, I may build the second layer around this central atom, I may build a third layer and a fourth layer at each stage, making sure that this kind of a polyhedron is maintained. Now, if I calculate the now my shell number is n, that means the number of atoms I am adding at the nth shell, the number of atoms nt and the number of surface atoms is what we are going to track. The total number of atoms is given by nt, the total the fraction of or those atoms out of these, which is ns being a subset of nt, is the atom sitting on the surface. At level 1, of course, we see that we of course use this formula for n greater than 1, but currently we will ignore the central atom and we will take all the atoms on the outer shell. So, we will assume that at n equal to 1 all the atoms are on the surface, and as we increase the shell add more and more concentric shells, we will see that only a fraction of these atoms actually sit on the surface and the remaining interior atoms will be treated like bulk atoms. So, if you now calculate the total number of atoms, a formula like this can be derived, wherein the number of atoms, total atoms, when I have a shell number n, is 10 n cube minus 15 n square plus 11 n minus 3, one third of that, and the number of surface atoms can be given by 10 n square minus 20 plus 12. So, therefore, if I put n equal to 1, I will see that the number of surface atoms is 12, which is the same as the number of bulk atoms, or if you want to add the central atom, the bulk atom will be one more in number. That will be one bulk atom and the remaining will be surface atoms if I take into account the central atom also. So, now what happens if I track this number of total number of atoms, the number of atoms which sit on the surface, and better still the percentage of atoms on the surface. So, here I am making up what is known as a bottom up approach. Therefore, I track the number of shells here on the x axis. So, I start with 1 shell, 2 shell, 3 shell and go up to a small number of shells, say for instance about 12 shells. So, here I am maintaining a polyhedral shape at each stage. The first stage of course is the what you might call the coordination polyhedron around a central atom in a cubic close packed crystal, which is a cuboctahedron, and when you go higher and higher up, there are the symmetry remains the same for the coordination shells, but you have more and more atoms being added, and at those stages you will see that the fraction of the surface atoms is going to reduce, or as we plot here, the percentage of the surface atoms is going to reduce. So, let us see first the total number of atoms, which is given by this curve here, and as you can see, obviously it is a cubic function, then it increases. Initially of course, you start with the number of atoms on the surface, and I will mark this number of atoms on the surface by a red line. You see that the number of atoms on the surface is 0. Of course, if I want to treat and you can see that the number of atoms on the surface is going to increase drastically. So, after a few truncations, say for instance about 12 truncations, now if I see the number of percentage of the atoms sitting on the surface, you see that the percentage actually decreases. So, this percentage surface atoms is on the right hand side. Initially of course, when I have for instance just one layer, I could treat all the atoms on the surface as total number of atoms. So, you will get 100% atoms sitting on the surface. Of course, we initially take that the one atom sitting inside the bulk, but you see that as we increase the number of layers, the percentage of atoms comes down, and only about 20% of the atoms are actually sitting on the surface by the time you are in 12 layers. So, it is very clear that in the bottom up approach, as I add more and more shells, the percentage of atoms sitting on the surface is going to drastically reduce with the number of shells I add, and this implies that the effect of surface atoms is also going to reduce, and the energy of the particle is correspondingly going to reduce, because in the overall Gibbs free energy the surface contribution is going to be less, and I will find the atom the particle is more and more stable as I go to larger and larger sizes. Now, just to put these things in numbers, if I have number and I am trying to go to large numbers here. So, I am starting with about 10 shells, which we had considered in the previous graph, and going up to say about 10,000 or more shells. When it is about 10 shells, the total number of atoms is about 3000, the number of surface atoms is about 812 or 800, and about more than 25% of the atoms are sitting on the surface. So, it is a drastic fraction of the atoms which are sitting on the surface when I have 10 shells. But you can see the reduction when I go to about 100 shells, the fractional percentage of the atoms sitting on the surface is only 3%. And suppose I am talking about 10,000 atoms, this fraction is very small, and for many calculations related to energy etc., I may want to effectively ignore this surface contribution to energy. So, but this is not possible obviously when you are in the regime of about 100 shells, wherein there would be a correction involved to the total number of atoms which are not having their bonds fully satisfied. Okay. Essentially, the increase in numbers in the percentage surface atom directly relate to the enhanced surface activity, thus leading to improved catalysis, chemical reaction, diffusivity, biological response, sensitivity, etc. Therefore, it is very clear that many of the what you call the important effects which can come because we are using nanomaterials comes from this aspect of the what we may call the surface, and this can be safely put into this category, which we had seen before in the classification, as change in size can directly lead to a change in performance, and this performance, as we just now pointed out, could be adsorption of gases. But here we are effectively ignoring the fact that when you are reducing the size, in fact the specific surface energy could actually change, and if there is a drastic reduction in the specific surface energy, then I may have to use this root C, wherein my change in size is going to lead to change in specific surface energy, which will further lead to a change in performance. So, this is at least two of these classes are nicely explained by the fact that when you make a volume calculation or the number of particles calculation, we see that there is a drastic change. Now, so far we have considered, for instance, two geometries, which is the geometry of a spherical particle or the geometry of a what you might call a polyhedral particle, which we considered was a cube-octahedral kind of starting shape. In general, of course, we will, as we have seen when we classified nanoparticles, we said they can come in very many different kind of geometries. There can be nano flowers, nano bows, nano strings, nano rods, etc. So, three of these general shapes I have taken up here, and obviously this is not an exhaustive kind of a list out here, but I want to see that what can happen when I have these three kind of general kind of shapes with respect to their trend lines as you reduce the particle, and here we are, of course, we are interested in the area per unit volume. So, the shapes we have considered here are sphere, cylinder and cube, and we are tracking the surface to volume ratio. For the case of a sphere, the area is given by 4 pi r square and the volume is 4 by 3 pi r cube, and therefore, we have already seen that the area per unit volume is 3 by r. That means, it is an 1 by r kind of a dependence. For a cylinder, and now I am talking about reducing the diameter of the cylinder. Of course, we can also cut the cylinder in its length. I may take a cylinder, and to produce a nano dimensional particle, I may actually do cutting at various stages. I may cut here, then I may cut here, then cut here, then cut here, and therefore, I will obtain a disc which is now nanometric in thickness. But that is not what I am doing here. I am actually reducing the radius, and therefore, the critical parameter I am tracking here is the radius. And now I am seeing how does the area per unit volume change as I am reducing. So, the h remains constant in this case. So, my area is given by 4 pi r square h, the volume is 2 pi r h, and therefore, the cylinder would have A by V as 2 by r. For a cube, there are 3 dimensions, and of course, I am still maintaining it as a cube as I am reducing the dimension. I am not changing its geometry, and I can track my A by V, and I can see that the area is 6 L square, because now I have 6 of these surfaces. The volume is L cube, and therefore, it is a 6 by L. So, it is clear by considering these 3 geometries that if I am talking about different kind of critical, various types of critical dimensions, and of course, when I mean various types, here I am talking about the radius of the cylinder, here it is the radius of the sphere, and here is the edge of the cube, the functional behavior is very, very similar. Of course, we can clearly see that the factor involved is very different. Here it is a factor of 6, here it is a factor of 2, here it is a factor of 3, but for these simple geometries which I have considered here, the functional behavior is very, very similar. But just because the functional behavior is similar, I should not conclude that the enhancement in property or any one of those things is going to be similar, because of some reasons which are obvious by looking even at these geometries. Here, for instance, the number of dimensions in which the curvature is increasing is just 1. So, the curvature is increasing in one dimension, effectively the curvature is flat on the other dimension. Therefore, more and more bonds will be unsatisfied in the direction of the curvature due to this curvature, but the other direction it would be a flat kind of a dimension. But in the case of sphere, the curvature is increasing in all 3 dimensions. So, as the particle size is reduced, there is more and more bonds of the atom sitting on the surface which is going to be unsatisfied, and therefore, the energy of this particle and the reactivity of these particles may be more. In the case of a cube, as you can see, there is no change in curvature involved, because all surface faces happen to be flat and they continue to be flat. And but the important point to notice here is that the topology of this kind of an object tells you that there are certain lower dimensional entities to be taken into account when you are dealing with a cube, like for a cube has an edge. An edge, atoms sitting on the edge obviously have bonding much worse than that of atoms sitting in the face. So, and the other point to be noted is the corner, and bonding of atoms sitting on the corner is going to be worse than that of the atom sitting on the edge, and therefore, if I have a single cube, I have only of course 8 corners, but suppose I am not reducing the dimension of the cube, but splitting this cube, then I will notice that more and more atoms will actually sit in the corner, and therefore, just by merely looking at the functional dependence, I cannot conclude that all the properties changes will be identical. The property changes will obviously depend on the specific geometry I am considering, and as you can see here, the geometry puts in additional parameters which I need to consider. For instance, the dimensions in which the curvature is going to change, the number of lower dimensional entities in the object, like for instance an edge or a corner, and for instance in more complicated situation, even a surface may have additional entities like ledges and surfaces, ledges and kinks, about which we will talk about in an upcoming lecture. Therefore, the summary of this slide is that I need to talk about not only a reduction in particle size, I need to talk about various geometries which can lead to my nanoparticles. For instance, I may take a nanowire and actually split it into make a nanoparticle, and the effect of a specific property coming from specifically these kind of a reduction in dimension. One small error of course in the case of cylinder is that actually the formulas got inverted. Now we have actually, this is the volume of the cylinder, and therefore I need to invert this formula to get my functional dependence, which is now 2 by r. Now we have seen some of the advantages, some of the beautiful things about the nano world, but we would like to list comprehensively, or as far as possible, the disadvantages and challenges which face us when we are entering the nano world. These are as important as actually knowing about the advantages, and as we shall soon see that more often than not, in the excitement of a new discovery, we may actually miss some of the problems which are associated with this, which can actually be potentially harmful in the long run. So everything is not rosy about nanomaterials. There are many shortcomings and challenges which need to be addressed for successful and widespread use of nanomaterials. So what are these challenges? Well, let's list them. So the issues related to nanomaterials are, first and foremost, difficulty in synthesis and isolation. To start with, synthesis of nanostructures, nanoparticles and nanomaterials is considerably more difficult as compared to their conventional bulk counterparts. This is of course needless to say, because here we are talking about a dimension which is extremely small, and therefore we are actually going to put in considerably more effort in actually synthesizing nanostructures and nanoparticles. Additionally, if the synthesis of nanoparticles has been carried out in a solution, it is extremely difficult to retain the size of the nanoparticles. So once having synthesized, it often becomes a challenge that we have to retain the size, and retain the size of course during synthesis, and later on of course, as we shall see, during the service of the actual nanoparticle in certain intended application. In applications where the particles need to be of the same size, obtaining a narrow size distribution poses additional challenges. More often than not, we do not want particles of various sizes to coexist, because if I am depending on, for instance, absorption of a specific wavelength, or I am talking about a certain other kind of a property which is now going to be dependent on the grain size, if I have too wide a grain size variation or too many particle sizes involved, then I will obviously not get the specific property enhancement which I am looking for. Therefore, I want to get a narrow size distribution, and this is definitely a challenge when it comes to nanomaterials. In polycrystalline materials, example, for instance, I am talking about the grain size in nanometers, grain growth can take place during their processing. So as we already said, if I am talking about a nanopolycrystal, then the interface area is very large, the grain boundary area is very large. This automatically implies that the diffusion is going to be very large along the interface, and grain growth can also take place. This means that even though I have synthesized my nanomaterial, before I even put it into application, I would see that the grain size would have increased, and I am no longer having a nanostructured material, but I would be having a grain size which could have already increased to a micron size, and this would imply that the nanoscale has been destroyed. For example, when bulk nanostructured materials produced by sintering of nanocrystal, grain growth becomes a serious issue. There are many synthetic synthesis techniques, and alternate lectures may talk about them in this course, wherein I have not produced a bulk nanostructured material, but I have actually produced a powder which has either the powder grain size itself, either the grain size is in nanos, meters or the particle size in nanometers, and when I want to synthesize a bulk material out of this, I need to sinter the material. And when I am trying to sinter, obviously I am exposing the material to high temperatures. So, this will lead not only to sintering of the particles, but also it may lead to, for instance, loss of nanostructure, and this means that certain conventional techniques may not be suitable for making nanostructured materials. The second issue I have to deal with is the instability of the particles. Nanoparticles, especially metal nanoparticles, are very reactive. In fact, in some cases they could be so reactive that they can even lead to an explosion. So, there are safety issues also involved here, i.e. they are thermodynamically metastable. And as we just made a calculation, we know that this is an increase in the surface area, and with the increase in surface area, the number of atoms who are poorly bonded increases, thus making my nanoparticle very reactive. The kinetics associated with nanomaterials also rapid, like we already seen with respect to diffusion. Surface diffusion plays an important part. Fine metal particles can even be explosive owing to the high surface area coming in direct contact with oxygen, which is now an exothermic reaction. So, when I am dealing with these nanoparticles, the reaction need not be slow, it can even be explosive. Nanomaterials have a poor corrosion resistance and are prone to phase change. We already seen that when you reduce the particle size, then actually a different kind of crystal structure may be stabilized, and additionally because of the large surface area, they are poor in corrosion resistance. Hence, it is challenging to retain particle size in the nanoscale and to maintain properties of the nanomaterials during service in an intended application. And when you are talking about an application, this may actually involve long time scales. So, we are talking about actually a service component in service, and therefore, we are really talking about large time scales. Okay. The next issue related to nanomaterials is the presence of impurities. As stated before, nanoparticles have very active surface leading to adsorption and absorption, and I am talking even of gases. Additionally, once a species has been adsorbed on the surface of a nanoparticle, the path length for diffusion required to take the species to the center of the particle is small. Even this aspect we have talked about before. That means that the entire nanoparticle may be easily contaminated, and this is a serious issue because the species being adsorbed on the surface is soluble in the material. It will be taken to the center of the nanoparticle, and the entire particle may now be contaminated with respect to the impurity, which might have obviously a deleterious effect on the properties I am considering. Often nanoparticles are very reactive as well, thus making it very difficult to maintain a pristine surface. And when I am talking reactive, actually there could be formation of oxides, nitrides, etc. on the surface, and hence it is not only challenging to synthesize pure nanoparticles, but also to keep it pure during service in an intended application. So, this is a very serious issue with regard to nanoparticles, that I have to protect it in some way from allowing impurities to come on the surface, and this is not only to be done during synthesis, but also during an intended application, which could involve long time scales. The next issue is that many of the nanoparticles or nanomaterials having a nano entity could actually be biologically harmful. Nanoparticles can be potentially harmful as cell dermis is permeable to them. These sizes being so small, they may actually get into the human cell or a cell of an animal or a cell of a living being, and there may be no natural defense to the penetration of these particles into the biological system. Toxicity of nanoparticles is enhanced due to their high surface area and activity. Here of course, I am talking about two kinds of particles, which are of course benign in the micro scale, but become somewhat toxic when you go to the nanoscale, and those other particles which are toxic anyway in the macro scale. Therefore, when you go down to the nanoscale, they may tend to become even more active and therefore even more toxic. Hence, nanoparticles have been shown to cause and examples of these kind of bad effects is one of these is that nanoparticles have been shown to cause irritation to tissue, and they can even be carcinogenic. If inhaled, they may be entrapped in the lungs and they cannot be expelled out of the body. Their interaction with liver blood could also prove to be harmful. So, there are a lot of studies which need to be carried on further to actually establish the toxicity of these particles, their interaction with various kind of cells in the body, their not only short term acute effects, but also the chronic effects coming from repeated exposure to these nanoparticles. And this area of biological what you may call the effect of nanoparticles, of course originally not intended even to be like it is not a drug delivery particle or one of those particles which is originally intended to be put into a human system or an animal system. Their effects is or studies on these aspects is barely begun, and therefore, and especially the chronic studies are nowhere near complete, and therefore we really do not know that what wrong could happen if some of these particles are somehow entrapped in a human system, like we said, in the lungs of a human being, as we had pointed out. And more importantly, how much of such a material could be tolerated by the body is also not known. Therefore, this biological aspect needs lot more of study, and we need to characterize various kind of nanoparticles that we are producing for totally different applications in terms of their, for instance, effects on a human system or an animal system. Another area which is again lacking considerable study is the recycling and safe disposal. Given that the age of nanomaterials has only just dawned, that means we have just barely scratched the age of nanomaterials, newer kinds of nanomaterials are being discovered virtually every day, and hence there is a lack of availability of set procedures or policies for safe disposal of nanomaterials. Often initially, of course, these nanomaterials are just made in a few milligrams or even smaller quantities, and therefore nobody is really worrying about what will happen if this kind of a material were produced in a larger quantity, wherein we have to worry about issues like recycling or even issue of how do we dispose of these particles once, of course, my research or my intended testing is over. Issues regarding their toxicity are still being hotly debated, and detailed studies of exposure experiments are not yet available, and this we had cited as an example when you talk about the biological effects. As most of the current research and studies are devoted towards developing newer materials and allied technologies, very little thought has been put into aspects like recycling and safe disposal. So, the current shortcoming is not that we cannot study them, but most of our efforts are not going in this direction. We are just trying to develop new materials, we are trying to put them into newer applications, and we are never, there is no what you might call pause and question being asked that what if such a material were to come into human contact or in contact with other living organisms. And hence these issues need serious and immediate attention. So, this is one of the areas where it is almost imperative that we do a lot of research, we do a lot of studies regarding safe disposals, regarding recycling, and also regarding the effect of nanomaterials on various kind of living beings. So, unless this aspect is conclusively proved that there is a beneficial effect without what you may call much of deleterious effect, and if there is a deleterious effect, then how do I deal with it, the age of nanomaterials can fully never be beneficial. So, there are some challenges which we need to address before nanomaterials can find widespread use, and these challenges, which are basically coming from some of the issues which we have already stated, are consistency in quality. We need consistency in quality and control over chemistry, size, structure, microstructure, and morphology of the nanomaterials. So, variety of these nanomaterials have been produced in small quantities, but when we try to scale up the production, we need a control over the quality of these nanoparticles or nanomaterials, and we need a control over their chemistry, we need a control over their size, we need to control over their structure and microstructure, and finally the morphology, when we begin to say that okay, we have understood all aspects of nanostructured materials. We need fast and inexpensive characterization techniques. At the research stage, it's of course there is not a problem at all. I may actually use techniques like transmission electron microscopy, wherein it's a time consuming costly kind of procedure which I am using, or an atomic force microscope or Auger electron spectroscopy, which are very costly equipments, very what you might call involving lot of at times lot of specimen preparation before it material can be put for testing. But in the long run, I need fast and inexpensive characterization techniques to ascertain if the parameters mentioned above, like chemistry, size, structure, microstructure, and morphology, have been achieved. Fast and inexpensive characterization tools need to be developed. So, when in a factory production line, for instance, I cannot use any of these tools to characterize my material which is coming out of the assembly line, and therefore I need some newer techniques or modified version of some of these techniques which will give me a fast characterization, a fast handle on all these various properties and parameters which I need to control. This is keeping in view the effort and cost associated with some of the current techniques. So, there is the capital investment, the specimen preparation time, the amount of material which can be tested at a single time, all these are poor in some of these techniques, and therefore definitely we need some inexpensive characterization technique which can give me quick results, and quick results I mean sometimes even when the assembly line is rolling. So, further challenges which we need to address is the scaling of production. Often synthesis of nanomaterials require special processing and techniques which can restrict the thickness of bulk nanostructured components to a few millimeters. As the size increases, prolonged heat treatment results in grain coarsening and loss of nanostructure. Eventually, either secondary processing is required to break down the bulk structure into nanostructure, or we require multiple processing to retain the initial nanostructure. Hence, scaling of production remains a challenge. For example, if I were to use MOSI2 nanoparticles as a nano ball bearing, the production can easily be scaled up to a few kilograms. When I say easily, of course, I do not mean very easily, but definitely with some effort we can actually scale it up to a few kilograms. But for successful commercial application, this needs to be scaled up a few orders of magnitude. So, it is very clear that in some niche applications where I need very small quantity of material, nanomaterials are already achieving quite a bit considerable amount of success. But for a what we might say widespread application of nanomaterials, it is clear that I need to have a scaling of production. I may be talking about tons of materials being produced, and each of these tons or batches actually has somewhere at its heart a nanostructure or a nanomaterial or some length scale which is nano, and each one of them obviously is going to have some special property, and either during my synthesis or during further processing to actually take the material and make a component, I should not have a loss of nanostructure. So, these are some of the challenges which are very serious and have to be addressed before we see that nanomaterials and can be used in a day-to-day life in a widespread manner. If, as we have noted before, that most of the time nanomaterials and nanostructures are not produced by the usual routes used for producing bulk components. Suppose I were to produce for instance a bulk component, I may use something like an injection molding or a simple casting or some kind of a forging. But we would notice that when you want to produce nanostructured materials, for instance, suppose I want a grain size in the order of nanometers, I may use some severe plastic deformation technique, and when I am talking about severe plastic deformation, then I am limiting myself, I am introducing a new processing technique and not relying on my conventional processing which I have used over the years for conventional production. So, one way is to co-opt these techniques, the conventional methods, in a new form to actually produce nanomaterials. If existing processing techniques can be put to the use in the case of nanomaterials, this would lead to considerable savings in effort and cost. Conventional processing techniques typically involve long time scales or high temperatures, but as nanomaterials are not thermodynamic in a state of thermodynamic equilibrium, there is always a tendency for grain coarsening or phase transformation. Hence, or in other words, a loss of the nanostructure in the general sense. Hence, it is imperative to develop variants of current techniques which involve high pressure and low temperatures, and which also will give me nanostructured bulk material in a short time scale. So, not only do I have to scale up the production using the new techniques I have developed, but also try to somehow co-opt the existing techniques by modifying the processing parameters, by modifying various processing steps, so that I can use them as well in production of nanostructured materials. The obvious advantage would be that I can use my existing production lines, I can use my existing capital investment with of course modifications to them. Therefore, I would have a considerable saving in terms of my overall integration of the new technology into an existing production line on an existing industry. So, this is another challenge which remains in front of us, and very few people are actually what you might call working on these areas where they are trying to use existing processing methods to get nanostructured materials. One class of materials which we have seen which are very interesting but are equally difficult to synthesize are the hierarchical structures. Biology, as we noted, is abound with some of these hierarchical structures, but when it comes to production of these, this definitely is a big challenge. As we have seen that structures at various length scales combined in a hierarchical fashion to provide an exceptional performance at the bulk scale. At the same time, features represent these individual features represent various length scales like nano, micro and bulk are essentially to allow for their synergistic contribution. So, these various length scale give rise to a synergistic contribution. For example, we have seen the nacre structure is composed of calcite layers glued by nano layers of protein in a cement brick platelet structure, which provides for its exceptional toughness or an impact resistance. But engineering such a structure has appeared almost next to impossible because the arrangement of nano platelets with an interlayer of a soft material like glue like material is highly complicated. Further, it is not that I am just going to arrange these layers in a one localized region, but I need to arrange them in a larger length scale so as to give rise to different orientations that allow retaining this composite structure with exceptional toughness in spite of the constituents being brittle. Hence, hierarchical synthesis across different length scale poses even more serious engineering and manufacturing challenges. So, when it comes to normal nanostructured materials where we have a single length scale to deal with, it is difficult enough, but when I am talking about a hierarchical structure, these issues are compounded, the manufacturing issues, the issues of even making it in a lab scale becomes even more difficult. So, it is very clear that in spite of the exceptional properties I get from hierarchical structures, if I have to see them used in a real industrial scale, then I have to worry about much more serious issues. Many of you must have been exposed to the fact that I need to manipulate nanoparticles and nanostructures. So, this manipulation is itself an issue. Often nanoparticles, nanostructure need to be handled individually, and further these need to be arranged in a precise way. And here of course I am not talking about those kind of nanostructures and nanomaterials which are comes under the class of self-assembled nanostructures. Therein of course in the case of self-assembled nanostructures there is a propensity for the material itself to arrange in a particular configuration given a certain kind of a processing condition, and there of course I don't have to worry about arranging these nanoparticles in an external way. But here in normal cases I may want to arrange them, I may want to manipulate them, I want arrange them in a very precise configuration, maybe in 2 dimensions and sometime even in 3 dimensions. The manipulation of individual nanoparticles requires a probe to pick, then to hold and translate, rotate the nanostructure, and hence control the control unit must be equipped with the nanometer size forceps like structures. So, I need some kind of a manipulator which is nano sized, which can hold these particles, translate it, rotate it if necessary, and locate it in a precise position in my assembly. And of course, this has to be done without damaging or altering the nanostructure nanoparticle. So, I have to obviously keep my nanostructure pristine while the entire processing. This is a challenging task requesting sophisticated instrumentation, and hence handling of nanomaterials into certain organization becomes highly challenging. And needless to say that when I am actually dealing with single nanoparticles being arranged in an array, obviously the process is going to be time consuming, and this is not what you might call amenable to mass scale production. So, we have to come up with newer techniques wherein I am able to actually do such a process in a fast time scale, so that I am able to produce many of these components which is done by a precise arrangement of these nanostructures or nanoparticles. Perhaps we have already talked about this aspect when we said that that we need recycling and safe disposal, but we just reiterate the aspect here that recycling still remains a serious issue. Nanomaterials tend to agglomerate, and the recycling does not face a problem in this regard. But when used without proper control, especially if released into the atmosphere or into the water system, their effects could be highly deleterious. And especially in this regard, the important problem remains that there are not enough studies to conclude that if they are even deleterious or not. So, this aspect is not even being studied in the case of many nanomaterials. Hence, certain policies not only using but also disposal of nanomaterials need to be evolved. So far there are what you may say, there are no strict norms for using them, there are no norms for recycling them, there are no policies with regard to government that what kind of nanomaterials can be released into the atmosphere, what kind of nanomaterials need to be protected, what kind of nanomaterials need to be agglomerated before they are released, and what kind of other procedures need to, especially we need to evolve with regard to nanomaterials. And now we are talking about policies extending across countries, which is what is currently lacking. Selectively isolating nanomaterials and evolving procedure for the recycling is going to be one of the important challenges ahead. So, the challenge is one of scientific importance and also one of, as I said, governmental policies, which is now going to play a very important role in the coming years when we are talking about widespread use of nanostructures and nanomaterials.